problem, we have electrical heating of the rod that's generating energy. Now this rod was at a uniform temperature, and this temperature is being raised to a point where it's higher than the temperature in the surroundings and the ambient. So we have temperature, because the temperature is higher in the rod, second law of thermodynamics says heat falls from high to low. Thermal energy falls from high, large amounts of thermal energy, to low. This is how the diffusive process happens. So if the rod is at a higher temperature, that means all the energy is going out. So we don't have any energy going into our system. Energy going in is zero. So now we're left with the energy balance where we have the energy generated minus the energy that leaves equals the energy that's stored. Now we're on a mission to find a relation for the change in temperature with time. Now some of you may remember earlier in the lecture what the energy stored looks like, and there's a derivative of temperature with respect to time. So we know, if we remember that we're going to be working with this equation now and manipulating it by representing the stored energy as we did before, and then inserting the appropriate rate equations to characterize the energy leaving the system, and then representing the energy generated via or by way of the electrical heating with an appropriate relation. Let's start with the generated energy. So energy generation, we can represent that in this course, and we will, either by Q dot or Q double prime. And this is basically a volumetric heat rate that is going to be in units of watts per meter cubed. This means that you're generating this heat uniformly within a volume. Now this is opposed to heat rate, Q by itself, which is in units of watts, or heat flux, which is the watts per area on a surface. And that Q has double prime. So we have Q with no prime, Q with double prime, and Q with triple prime. Now you're probably wondering what happened to Q with one prime. Well, you'll see that in this course as well. Not as often, but you'll see it, and that's just watts per meter. So that's the heat rate per unit length. So this is how we'll represent this in this class. Generation will be Q dot or Q triple prime, watts per meter cubed. Heat rate, which we've already seen for the rate equations, is Q in watts. Heat flux, Q double prime, and heat per unit length, watts per meter. Now I want you to write this down. I'm not going to write it on the board. So you write this down and also look in your book, and it has it listed. So that was a slight tangent. So let's get back on course. So we have our heat rate, and in this case our Q dot equals resistive heating. That's I squared R. So we're given a current and we're given a resistance. And this is the equation for resistive heating. The current squared times the resistance. And because this is a volumetric effect, we're dividing it by the unit length, 1, times the cross-sectional area, pi d over 4. Now, we just can't plug this into our energy balance because our energy balance is in terms of watts. So in order to get our Q dot or Q triple prime in terms of watts, we have to multiply this times the volume. So now we have that our E generation is equal to Q dot times the volume, which is equal to I squared R. L, and L is the length of the rod that we're considering. So I skipped some steps, but I'll let you work through that. You can see it in the book also. But you cancel out the area, and you're left with that as the heat generation term. So now let's look at the energy out. Energy out, once again in watts, we can equate directly using to the rate equations that are appropriate for the problem. And I've already talked about them. So we're going to have convection from the surface to the ambient, and we're going to have radiation between the surface of the object, the rod, and the surroundings. So this energy out is going to equal Q conduction. I'm sorry, that's incorrect. Q convection, which is in watts, plus Q radiation in watts. And these equal the heat transfer coefficient times the surface area of the rod times the temperature at the surface minus T infinity, which is the ambient temperature, plus the radiating heat flux, emissivity times Stefan-Boltzmann's constant, 5.67 times 10 to the minus 8, right? What are the units? I'll let you check what the units are, but remember that, Stefan-Boltzmann's constant. Once again, this is over the surface area of the rod, and this is times, multiplied times, the surface temperature to the fourth power minus the temperature of the surroundings to the fourth power. So this is what our E out equals. And all we did was we took our rate equations and we inserted it or equated E out to that. And basically when we put all this together, E out will be replaced by these two rate equations. So we have one more, energy storage. So we worked through this one before, but here again, energy storage, because we're neglecting kinetic, potential, and latent energy, we're only left with sensible energy, which is the thermal, internal energy. And the energy stored is the rate of change of that internal energy with time, which also equals the rate of change with time of the density times the volume times the specific heat times the temperature. Temperature and internal energy are related. Basically, things that have a higher temperature have more internal energy. They have molecules that are moving with more kinetic energy. And we can rewrite this as that. And basically, that's just stating that density, volume, specific heat are independent of time. We pull them out, but we know the temperature changes with time. And that's what we're trying to figure out in this problem, is the rate of change of temperature with time. We want a relation for that. So now when we put all this together, let's put it all together. We're plugging in our rate equations for E out, our expression for the generated energy,